In this section, we are going to compare the difference between open loop control and closed loop negative feedback control. And also, we are going to analyze why introducing negative feedback can well suppress the impact of disturbance to the output. So first, we look at the negative feedback. We have just analyzed for a typical pulse width modulated converter, we can express the output voltage signal as the sum of 3 parts. One is reference part, 1 over h, t over 1 plus t. Secondly is the line input part, GVG over 1 plus t. Thirdly is the load variation times Z out divided by 1 plus t. So H is the sensor's gain, GVG is a line to output gain, and Z out is output impedance. And also we have the T, right, where T is the loop gain, right? Is the loop gain, so equals to Hs times G compensation, G control to output, divided by Vm, which represents the PWM block. Correspondingly, we also list the analytical expression for open loop control. For a open loop control, we no longer have the sensor part and the reference part. The output signal is mainly determined by 3 parts, right? One part is the controlling part, GVD times small signal input, controlling input. Secondly is GVG times line input. Thirdly is the output impedance part, Z out times. Okay, so now let's see what difference do they have in reacting to the disturbances. The first disturbance comes from line, right? We have the line to output disturbance. For the negative feedback system, we can write the line to output transfer function. So this means that the ratio between output signal and the line input. When we consider the impact of line input, we will assume that the other small signal are equal to 0. And VREF small signal and iLoad small signal are both 0. So inserting those 2 zeros to this equation, we can obtain the ratio between output and line input, which is GVGS times 1 over 1 plus T, which is the loop gain. And similarly, we can also analyze the line to output transfer function for open loop control. Given the condition that the control signal and output impedance are both 0. Controlling input and the load variation are both 0. So you will see that this just equals to GVGS. To compare, we can see that the negative feedback will introduce a 1 over 1 plus t term for the closed loop control, right? And next, let's analyze the impact of the load changes to the output signal. So this, we call it as output impedance. So for the negative feedback control, so this is denoted as how the load variations affect the output voltage as the ratio of Vs and Iload small signal, given the condition that the other small signal are both zero, Vref, Vg, 0. So inserting those two zeros to this formula, we can see that this just equals to the output impedance times 1 over 1 plus Ts. Similarly, regarding the open loop control, we can also write the output impedance as output signal divided by load perturbation, given the conditions that controlling input is 0, line input is also 0. So this is relatively simple, just equal to the out. Also, to compare, we can see that the negative feedback introduce a 1 over 1 plus T term, right? Both line to output and output impedance, they contain 1 over 1 plus T term. And this is what open loop does not have, right? So if the loop gain Ts is large, what will happen? If Ts is super large, the 1 over 1 plus Ts will be super small, right? This means that the GVG, the out for closed loop negative feedback control will be significantly reduced, right? GVG and the out significantly reduced. So what does this mean? This means that for closed loop control, it brings us benefits that if T is large, the line disturbance and the load disturbance can be well suppressed by 1 over 1 plus C times, right? And next, let's look at the reference to output part. So only the closed loop control has reference input. So we just analyze the negative feedback condition. So this corresponds to Vs over Vref. Given the condition that the other small signal inputs are 0. So when we insert those two zeros to this formula, we can see that this V over Vref will be equal to 1 over Hs times Ts over 1 plus Ts. Hs is sensor's gain. Ts is loop gain. So again, if Ts is large, or we say that if the amplitude of t is much, much bigger than 1, so this quantity will, the fraction will approximately equal to unity. We would have reference to output transfer function approximately equal to 1 over hs. So this means that the closed loop control will precisely control the output signal to follow, to be equal to the reference signal times the sensor gain, right? Which is a good circuit behavior. We can achieve a precise closed loop control of the desired output signal. Okay, now let's erase the blackboard. Okay, we have erased the whiteboard, and also I have moved those 3 formulas to the left corner of this board. And now let's look at those 3 formulas. We can see that they all contain one common denominator, right, which is 1 plus t. So which means that the t, which is loop gain, is very crucial for us to judge the behavior of the closed loop control. So we need to pay special attention to the loop gain, Ts. So now let's do the analysis of Ts. Ts is the loop gain transfer function for a typical power converter. And one very specific example for the loop gain will be such an example. So Ts for a typical power converter could contain 4 parts. First part is the DC gain as T0, which means that frequency equals to 0, the amplitude for the loop gain. And also, we typically have a quadratic pole response, right? So in the denominator, we can have such a quadratical expression as 1 plus s over q times omega p1 plus s over omega p1 square. And also sometimes we have the left half plane 0, so which we use 1 plus s over omega z to denote the left half plane 0. And we can also have an additional pole at omega p2, 1 plus s over omega p2. Okay, now let's try to construct the Bode plot for this loop gain transfer function. The x-axis is the angular frequency in log scale, and the y-axis is the magnitude of the loop gain, so 20 log. Here is 0 dB, and we mark here is 20 dB, 40 dB, 60 dB. For such a transfer function, it contains multiple terms. At a low frequency, the DC gain term will dominate. So at low frequency, we will have a high DC gain, which corresponds to T0. And here is the quadratic pole position, omega p1. At this quadratic pole, we would have a bump, and the bump height will equal to Q indicible. Then we would have the double pole response. So here we would have a sharp slope of minus 40 dB per decade until we reach the zero frequency here, omega z. Since this is a left half plane 0, so we would have the slope change from minus 40 dB per decade to minus 20 dB per decade. And then this minus 20 dB per decade hit the 0 dB, which correspond to the crossover point, Fc. And with frequency go even higher, it goes on to decay at minus 20 dB per decade until we reach a high frequency pole at omega p2. So this pole will enforce another minus 40 dB per decade phase change. So this goes to minus 40 dB per decade again. So that is the complete magnitude plot for the loop gain transfer function for such an analytical expression. Since all those three terms, they contain t, right? And we have obtained the magnitude plot for the loop gain t. Now let's try to see how can we approximate those two terms, 1 over 1 plus t and t over 1 plus t. First, we do the approximation here. First, we look at 1 over 1 plus t. So this can be approximated into two stages, depending on different range for the t. So for example, for the frequency below crossover frequency, if we look at the magnitude plot of t, so we will see that for f below fc, the t is very, very high, right? Much higher than 0 dB. So meaning that the absolute value for t is much bigger than 1. So if this argument holds, t is much bigger than 1, we can approximate 1 over 1 plus t as 1 over t. And the second condition is that for frequency higher than Fc in the high frequency range, right? For high frequency range, we will see that the t amplitude is lower than 1, right? So for this scenario, if t is much lower than 1 at very high frequency, then the t can be ignored. So this can be approximated as 1, right? So based on this approximation, we can construct the body plot of 1 over 1 plus t. So basically, we look at the low frequency first. For frequency lower than Fc, the 1 over 1 plus t approximately equal to 1 over t, right? So in log scale, right? So we can construct the magnitude plot for 1 over t will be the t mirrored to the downside. So we will have such a profile. And so this is marked as 1 over 1 plus t at low frequency. And for frequency higher than Fc, it equals to 1, right? 1 is 0 dB, so which corresponds to here. So the white chalk curve corresponds to the magnitude plot of 1 over 1 plus t. And when we observe this body plot, we can see that for low frequency, right, f lower than fc, it's kind of, there is a very high damping rate with like minus 60 dB, right, 60 dB. So this means that the disturbance, both the line disturbance and the load disturbance, they can be well suppressed or reduced. This is kind of desired feature. And secondly, for frequency higher than crossover frequency. So we look at the body plot here. The high frequency body plot for 1 over 1 plus t equals to 0 dB. So this means that for high frequency disturbance, there is no effect. On disturbances with frequency higher than crossover frequency. Okay, next let's look at the approximation for t over 1 plus t. Similarly, we also consider them in two segments. First segment is also for low frequency range, frequency lower than Fc. Then we will have absolute value for t much higher than 1. If t is much higher than 1, then 1 plus t will be approximately equals to t. So this fraction will be equal to 1. So 1 means that the V output over Vref will be roughly equal to 1 over Hs. So this means that the reference signal will have a precise control of the output at low frequency region. Okay. And then again, let's look at the second condition for frequency higher than Fc. Then we will have the absolute value for loop gain much smaller than 1. So this, if t is much smaller than 1, the 1 plus t will be roughly equal to 1. So this will be t over 1, which will be t, right? So for the high frequency range, again, we can write the transfer function will be roughly equal to t over Hs. So this will be equal, right? T contains the H part, so H can be cancelled, will be equals compensation block times controlling block divided by pulse width modulation block. So this clearly indicates that for high frequency, the reference output transfer function, the feedback has no effect. So the negative feedback majorly dominate for the low frequency range to maintain a precise control of the output signal to follow the reference signal. Okay, so now we can also try to plot its body plot for t over 1 plus t based on those two segments scenarios. For example, for low frequency, now let me use the blue chalk. So it equals to, try to use a different color, equals to 0 dB, 1, right? So this is the body plot for t over 1 plus t. And for high frequency, this coincides with t, right? Meaning that they share the same profile at high frequency. So this double line, both blue and white, indicate t over 1 plus t. Okay, that is the magnitude plot for t over 1 plus t transfer function. And this profile also agrees with our previous judgment. Right? Low frequency, we can precise control, and high frequency, the feedback has no effect. Okay, this section we have compared the difference between negative feedback transfer function and the open loop control transfer function. And meanwhile, we also analyzed at what condition the negative feedback can realize suppression of the input side disturbances. And next, we are going to study the stability of the negative feedback control.